Hey there, so in this video I'm going to be doing a crypto challenge from the Cyber Apocalypse 2022 CTF. I'm going to be doing the Three-Eyed Oracle challenge, which there is the info if you want it. So the cliff notes for this challenge is that we're going to be using a chosen plaintext attack, and given the flag is appended to the text that we control the size of, we can align the blocks up such that we can end up decrypting the flag a byte at a time. Now for this video I'm going to try and go maybe a little bit deeper. I feel like this is a good challenge to do that with, in that there's not any kind of like math or complex computer science stuff that you might find in other crypto challenges. Also, I feel like it's one, if you were new to crypto or you're new to CTFs, this is maybe you got to this one and it's one you can jump into and feel like maybe you were right there and you almost got it. There's like a ton of information out there on the internet about it, so there's opportunity to have spent a lot of time frustratingly trying to get this. And so I want to help anyone who didn't quite get there to really kind of understand what's going on and break it down so it makes sense. Also, it's like kind of the challenge. I mean, this is the first challenge with like real cryptography. I mean, it's AES, it's, a mode you could potentially even see out there. And then honestly, it's just kind of a rush the way these kind of challenges go, where you could just get to sit there and watch the flag decrypt a byte at a time. I don't know, it's probably just because I'm a big dork, but it makes me feel like some kind of cool hacker. But basically, yeah, if you didn't get a chance to experience that, I kind of want to help you get there, because, I don't know, it kind of makes crypto addicting. And the more people that do crypto, like, I don't know, the better the world is, in my opinion. So anyway, let's go ahead and jump in. Looking at the source code, we see there's not a whole lot going on with this challenge. Basically, it's just setting up the server and running it, and then when we initially connect, we'll be sent this kind of greeting message, and then it's just going to jump into this infinite loop where it's basically just going to accept a message from us, encrypt it, and then unless something goes wrong with the encryption, it is going to return the ciphertext output to us. So if we look at this encryption function, we see it's taking our message and converting it from hex into bytes, because when you're operating in these crypto primitives, the operations are always going to be on bytes. And it's creating a AES with a ECB mode under this key, which is just some 16 random bytes. And then it's taking our message and it's prepending to it a prefix that's 12 random bytes. And then it's appending our flag to it, and it's padding all that, and the blocks for AES have to be 16 bytes. So this padded message has to be evenly divisible by 16, and then it is encrypting that message and returning the hex string. So one of the things you might think about first when trying to, like, if you're like new to this and you're not sure what to do, is like the logical thing, right, is like, let's figure out what the key is. Somehow we're going to have to like hack this or break it, and we're going to get the key, and that's how we're going to decrypt it. Which kind of makes sense, right? Like, that's a perfectly logical way to think, because, well, how do you decrypt something without the key? But that's actually kind of one of the really difficult and tricky things about cryptography. If you've ever heard the expression, don't roll your own crypto, it's stuff like this is why, because you can feel incredibly confident and get careless because, well, you're using encryption, surely it's safe. But if you don't implement it correctly, it all goes downhill. So in this case, just the fact that we have an oracle that allows us, we can give it any plain text we want, and it's going to give us the decryption back. And just by doing that, we are going to be able to recover, by the fact that they appended the flag to it, we are going to be able to recover the flag without ever finding out anything about the key. And in fact, we don't even really need to, we don't need to understand AES at all, or at least the internals of it. And let's actually go over that for a second. So while we don't need to know anything at all about the internals of AES or how it works, there are a few things that is helpful to know. So it's a symmetric encryption, so that means the same key is used to encrypt and decrypt. it works on blocks of 16 bytes. So anything you give it, it has to be, any message you give it to encrypt has to be able to be chunked up into blocks of 16 bytes, which is why we have a padding function. So if you gave it a message that wasn't the right size, it pads it to the correct size. But for our purposes, again, we can just think of AES as some magic black box. We don't need to know anything about how it works. We just need to know if we give it a message and a key, it's going to give us an output. And the other thing is that basically the outputs, for all intents and purposes, are completely random. If we give it an input with the same key, we won't, from the output, we won't be able to tell anything at all about the input. And even if, so it's 16 bytes, so a block, an inputted block is 128 bits. If we change just a single bit in that 128 bits, the output will just be completely different. So even if we have two messages and they only differ by a bit, we cannot tell anything at all from the outputs that the two inputs were similar. It's also, obviously, right, it's deterministic. So if we encrypt something with the same key, we'll always get the same output, and that output will always decrypt back to the original input. And then if we look at what ECB mode is, so the actual AES would be happening in this right here. We can think of this as our magic little box, right? We're inputting the key, and then we're inputting a plain text, and we're getting out a ciphertext. And ECB mode works by, you just give it a single block, it gives you a single output. And then the next iteration, it just takes the next block, gives you the next output. And then at the end, it just, what we get back is these all just concatenated together. Now, ECB mode isn't really used anymore because it has a lot of properties that aren't good for what we're trying to achieve with cryptography. The kind of famous example here is this like picture. So this is encrypted under ECB mode. And since under the same key, any block is always going to produce the same output. Like when this was encrypted, all these pixel values are the same, right? So they're being encrypted and they're coming out, they're all going to be the same. So when you look at it, you can tell, like you'd never know what value it was, but you know all these values are the same. So it's like preserving a lot of information. And ideally, right, the way you imagine encryption, if you encrypt this picture, what you want someone to be able to get back is just complete nonsense. Like, well, not nonsense, but just complete random noise. So how are we going to use that knowledge to recover the flag? Well, if we look at the source again, we got our message sandwiched in between these things. We can make our message whatever we want. We can make it as big as we want, up to 4,096 bytes. But we control this completely. Now, what I'm going to do to explain it is also something I want to talk about, as I think is a helpful hint in these challenges, is that lots of times what you're going to get is a more complex version of something simple. And do it for a couple reasons, right? I mean, CTFs, it's hard to come up with challenges, so they'll often add just a little twist to something that maybe you already know how to do, but it just makes it a little more complex. But the problem is, if you don't already know how to do it, you're looking at a more complicated version of maybe the examples you're going to find and try to figure out. And that can like make it harder for you because you're trying to struggle to learn something and figure it out while also trying to make it fit into this more complicated thing. And so my advice is, don't do that. Make it simpler. Like, we don't have to solve the complicated version first. Let's solve a simpler version so that we can know that we understand it and that we've got it kind of figured out, and then we'll do the more complex version. So a simpler version here is, we're not going to have this 12 bytes of random prefix because that makes it harder. And also, oops, if I could type. Also, we are going to make the flag less than a block. Like, we don't know what the real flag is, but we'll make our test flag less than a block. So this would be the simplest version. So If we gave it absolutely nothing right now, we're just going to get back the encryption of the flag. And so working on our solution text here, I wrote these ahead of time. This is basically just we're importing pwn tools, which if you don't know what that is it's a Python package that's really helpful for lots of things, but kind of was designed specifically for like all these things you'll find in CTFs and stuff. So it's definitely something you want to get and learn a little bit how to use. So I'm basically just using that to connect to the local instance of this I have running. And then I wrote two helper functions. Since in cryptography, I always like to just work in bytes. So bytes in, bytes out, because that makes it easier than trying to like remember like, oh, the server wants it in hex. Is that byte string or whatever? When I do it, I do bytes in, bytes out, and then I make some helper function handle all that other stuff. So like in this case, it's going to get the server to the spot where it's going to accept it. Since the server is accepting hex, we are going to convert our bytes to hex, and then we're going to convert that to a byte string because that's what pwn-tools likes to use. Then we're going to send it. We're going to get the ciphertext back. We're going to strip off the new line character. And then since pwn-tools gives us a byte string, but from hex needs a string, we're going to convert it back to a string, and then we're going to convert it to bytes, and that's what we're going to get back. And then I just made this function to just print it out pretty kind of for the examples I'm going to use. It basically just carves it up to blocks. And then since byte strings with random values in it are kind of like hard to look at, it's converting it to hex. So it'll show it to us better. So like I said, if we just ran this, since our message is literally nothing, we get nothing plus the flag. So this is the encryption of what the flag is padded to a block. Now, like I said, AES is, let me draw it here. AES is deterministic. So if we give it the same key and the same plaintext, we will always get out the same ciphertext. So if we gave it a block of nothing but A's, what we'll get out is random gibberish, but it'll always be that same random gibberish. So we see, A times 16. So we give it 16 A's, so this is the first block, and then this is the cipher, or the block of the flag. Does that look different? I mean, it can't be, but it 117 F1. Nope. Okay. I don't know why. Just brain fart, I guess. I just want to make sure I didn't screw something up. Anyway, so yeah. Just goes to show my point, even though I didn't trust it. So this would be the encryption of all A's, and this would be the encryption of flag. And if we gave it, let's give it 3 blocks of all A's. Right? So we're going to see the first 3 blocks are all going to be the same because those are the encryptions of all A's and then the flag. So what would happen then if instead of that we only gave it 15 A's? And that means when it concatenated our 15 A's with the flag, what we would be encrypting is the first 15 bytes of A, or 15 A's and the first byte of the flag. Now it's going to be random. We won't be able to tell from the output. Right, this looks completely, here actually let's do it this way. So we'll do a block of all A's and then a block of 15 A's with the first byte of the flag. So we see there's our all A's. We know that's all A's right now because we can recognize it now that we know that's what a block of all A's looks like. This is a block of 15 A's and the first byte of the flag. And then now this is the rest of flag. So this looks completely different now, right? Because now it's not the flag, it's the flag minus the first byte. This is completely different. Like we can't tell anything like it might be tempting at first if you're learning about this to think like, okay, now we know this is 15 A's and the last byte of the flag, or the first byte of the flag, and we know this is 15 A's. Can we somehow use these two to figure out what it was? And just from that, the answer is no. Like, it's like I said, the output is completely, you can't distinguish anything at all. You can't tell anything at all about the inputs based on what the output is. But if we go back to here again, we know, right, we can control the size of the message, and we gave it 15 A's in the flag, and we said like, oh, well, we know what the output of 15 A's is, right? We could have a little dictionary up here and we could keep track of that, and we could go like, oh, 15 A's, that equals some random thing. We know what it is. It's this. Well, what if we gave it 15 A's and then a B? Well, we don't know what that is yet because we haven't done it, but we could do it, right? We could make this 15 A's. 15 A's plus 1B, and when we do that, now we know it's that, right? There's our flag again. That's the one that I didn't recognize from before. That's the same. But now this we know is 15 A's and a B. We know what that looks like now. Now we can't predict anything. You know, we won't know what 15 A's and a C looks like until we do it, but we can do it. So what if then we do every single possible byte value in this last one, and we tell the server to encrypt all those, and then we find the one that looks like this? Well, then what we will know is what the first byte of the flag is, right? We'll know what 15 A's and every single other possible combination of byte value looks like, and then when we do 15 A's in the flag, we'll be able to say like, oh, it matches up with, you know, we'll have a big long list of them, you know, dictionary, and we'll be able to take that output and go like, oh yeah, it's that one right there, whatever that was. So hopefully that kind of like makes sense and you see what we're doing, because we can then keep repeating that process. Like now after we've done that, like now we'll know, we know what the first byte of the flag is. This is what we know down here. We know flag 0. Well, now instead of 15 A's and the flag, or 15 A's, we'll give it 14 A's, the first byte of the flag, which we know now, and then we'll get the encryption when we do that. When we send it just that message, the first 15, it'll stick the next byte of the flag on the front, and then we'll know, since we'll know what the output of that is, right? We'll be able to see it. And then we can do the same thing we did before, except now instead of sending it 15 A's in every possible combination, we will send it 14 A's, the first byte of the flag, which we know, and then every single possible combination. And we'll do it just like we did before. We'll match that up and go like, oh, okay, now we know what that is. And then we just keep working our way back until eventually we've, you know, if the flag was super long, we would get down to where we had an A, and then, you know, all the ones we know, and then like whatever the last byte in the block of that flag was. So hopefully that makes sense. And actually, let's just go ahead and write that up. So let's go ahead, and we know it's less than a block. So what we can do is we could say, we'll call dummy will be our block of all A's, and then we want to go through each one of those, and we're starting at 1 because what we want to do is, so we'll call actual the one with the actual flag byte in it we want to decrypt. And what we're going to do is consult the Oracle dummy. We want everything up to the last byte, right? We want 15 A's, not 16. I guess I could just have made this 15, but in my head, it just, I don't know, makes more sense for me. It's easier for me to understand if I just like, that's a whole block. I don't know. It's less to keep track of, I guess. I don't know. But you could obviously just make it 15. And then, yeah. And then what we're gonna do, so that will be 15 A's in the byte. And then we want to test all possible byte values. So there's 0 to 255. And then, so our test block would then be the same ones, 15 A's, and then plus the byte, but we need to convert that into bytes because this right here for B in range 256, that's just going to give you integers. So we want to convert that to a byte string so that we can append it to our 15 A's. Now this would only work for the first block, right? So what we need to do is add how much of the flag we know. So the first time through we know none of the flag. And then, so this will be empty, so it will be 15, nothing of our flag, and then our test byte. We'll eventually learn what the test byte is. Let's actually go and do that now. Right, so this is going to be giving us back, same way here, we got 2 blocks back, but we're only looking at this first block. That's the one we want to compare to. So we're going to compare the first 16 bytes of the test block with the first 16 bytes of our actual, which is the one with the flag in it. And if they are equal, then we know that the flag, that byte of the flag was that value. So we will append that to our flag. And then we can break out of this loop. And so like the second time through, now we'll be doing 14 A's. So dummy -2, so that's 14 A's plus the 1 byte of the flag we know, which we know because we know it, it'll be an H. And then our test byte. And I don't need these. And I think that should work. Now another thing I want to, another tip I want to give is, like, if you're working on this and trying to debug it and figure it out and you're using the remote server like in the CTF to do that, you're much better off doing it locally. Like, I mean, look how many potentially we have to send 256 requests just to find a single byte of the flag. And, you know, depending on how long the flag is, we're sending a lot of requests to the server. So, you know, you're sending just a few requests a second. But if you do it locally, it'll go really fast. So here, let's actually do that. It would help if I printed it, wouldn't it? It actually took 9 seconds even without printing. I would have thought it would have gone faster. But anyway, this would take, oh wait, okay, so we do have, I did something wrong here. So 1 to 16, oh, there's what I did. So I need -I, not -1. So it only worked for the first one because then every single time I was doing it wrong. And that's why it took so long. I would have thought it took longer because it was, all of these were failing, so it was sending 256 every time. So anyway, so you can find it in just a few seconds as opposed to several minutes. And, you know, that adds up when you're debugging and trying to keep focused and all that. So I would definitely do it that way. Okay, so anyway, a few things to note. First, so sweet, we solved it in the simplest case, but we need to go over why there's that XO1, and that's just padding, but that's what I want to go over next, is the padding. And you might have already seen one problem we might have, in which case, what if the flag is longer than a single block? And if we just started out with a block of A's, we're decreasing our A's as we go along. Eventually, we're going to be left with where we've got the first block of the flag, but now we're out of A's over here, so we can't smush anything over. How do we get the rest? Well, I mean, the most obvious solution would be we just need to send a whole bunch of A's. So instead of a block of A's, we could send like 10 blocks worth of A's. We just need to make sure we have more A's than there are the length of the flag. That way we never, as we keep losing A's, we never run out. Now that definitely would work, but it's not the most elegant solution. The most elegant way would be, what if we just knew how long the flag was? And then we would know exactly how many A's we needed to do. And we can actually tell how long the flag is, and we can do that by knowing how padding works. So this padding scheme in this, I'm pretty sure, don't quote me on this, but I'm pretty sure it's PKCS number 7. And the way that works is, so like I said, every message has to be evenly divisible by 16. So if it's not, say you had a message that, this is just random, whatever, and the last byte, so it's only 15 blocks long, or 15 bytes long. And so then when you pad that, what padding does is it adds another byte. It adds 1 byte of the byte value 1. And if you had a different message where it was, say, 14 bytes long, it would add 2 bytes of the byte value 2. So if it was 13 long, gold star if you can guess, it's 3 bytes of the byte value 3. And on and on. Now, the other thing you need to know is that padding is mandatory. So if you gave it some message that was exactly divisible by 16, what it will then do is append a whole nother block of the byte value 16 times. And this might look like a 10, but it's in hex, so that's actually 16. So it's going to be 16 bytes of 16. And the reason for that is, if you think about it, so the way when it unpads something, basically all it does is it just looks at the very last byte, and then it knocks off that many bytes. So it sees, oh, it's 2, I'll take off the last 2 bytes. Now, if it's programmed correctly, it would look and it would make sure that this is a valid padding byte, and then it would also make sure that everything it's taking off is all the same. So it would look and make sure it was, and if it wasn't, then you'd get some kind of error that it's invalid padding. Which, side note, actually, just knowing whether or not a message has correctly padded or not can actually lead. You don't have to know anything about the decryption or any of that, or what the actual values are. Just knowing whether or not it has correct padding or not can actually lead to recovery of the plain text. Anyway, that's getting carried away there. And so, but the reason for this padding is mandatory is, what if your message, you actually wanted your message to end with X03, X03, X03? How would it know whether or not it was padding, or whether or not you just happened to send it a message that was perfectly divisible by 16 and you wanted the last 3 bytes to be X03? So the way it does that is, no matter what, there will always be padding. That way it knows it can always look at the last byte and unpad, because padding is required. So the way we can use this to recover the length of the actual flag is, so let's use an example where our flag is, I don't know, we'll say it's 28 bytes long. So it takes up 2 blocks, right? Because each block is 16 bytes. So our flag ends here. Here is like the little HTB. The last, the flag's going to end with a curly thing. And then the last 4 bytes, it'll pad it. So the last 4 bytes then would be X04, X04. I didn't leave myself enough room. X04. Now, what happens? So we know we're going to send, if we send it, if we were just to decrypt the flag back, say we don't know how long the flag is, and we encrypt it, we get back 2 blocks. So we know the flag is somewhere between like if it was 16 bytes exactly, we would still get 2 blocks, right? Because it would be a mandatory block of padding. So we know that it is at least 16 bytes. And it could be up to, well, we know it can't be exactly 32 bytes, right? Because then there would be a whole nother block we'd get back. So it could be up to 31 bytes. So it could be any of the values from 16 to 31. We don't know where it ends in here. Like in my example, I'm just showing it like we know, but pretend we don't know. Maybe I shouldn't even have done that, but whatever. What we can do now with the way we have it set up, right, is every time we send it an A, it's pushing everything over 1, right? So if it was in the example of 28 bytes, now it would be, we'd have an A. Oops, I should make them the same. An A, and then, right, everything gets pushed over. So now it would be at the end of the flag, and then XO3, 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 right? So we could keep doing that. We could keep adding A's. So we'd send another, now we do the same thing with 2 A's. And then it's gonna end in XO2, XO2, and then we'll send 3 A's, and it's just gonna need the 1 byte of padding. And then look what happens when we send 4 A's. Now all of a sudden, the flag ends on that last byte, and since padding is mandatory, it's gonna add a whole nother block of padding. So we went from, we're getting 2 blocks back, to all of a sudden, bam, we get 3 blocks back. And all we did was make the message 4, we added 4. So basically what we're doing is what we're adding on the front is basically eating up the padding. And then when we get to the exact right size, suddenly a whole nother block appears. So we can actually use that to get the flag because we know that at the start we got 32 bytes back. We kept adding A's, and then we got 48 bytes. So on our 4th A, we got a whole new block of ciphertext. So we know that originally there was 4 bytes of padding. So we could use that then to know that the flag was 28 bytes long. Hopefully that made sense. So basically all we have to do is send it nothing, and then see how long that is, and then keep sending it A's until all of a sudden now we get an extra block, and then we'll be able to figure that out. So for our server, let me kill it, and then we're going to do the same thing now, right? We're just making it a little bit more complicated. So we want to make our flag longer. We want to make it longer than a block. So let's do the same thing, and now we'll add let's add a get flag length function. So then what we could do then is we will send it, let's send it nothing. So our message will start out as nothing. And then so our initial size will be the length of what we get back when we consult the oracle, where we add our message of nothing. So that's how many blocks the flag takes up originally. And then what we want to do is we want to keep incrementing our message by a byte at a time until all of a sudden it changes. So we could say, wow, length of I don't need two parentheses. I'm used to having to put while inside of parentheses. Anyway, so length of is equal to initial size, right? We know nothing's going on, so we want to add a byte to our message. And then it'll keep executing this loop until all of a sudden our message was the same number as the padding, and then bam, we'll get a whole new block. It'll exit out of this loop. And so then we can use that to figure out how long the block was. So we will return the initial size minus the length of our message. And that is how long the flag is. So then what we want to do here is we're going to change our dummy from one block of A's to, well, first off, let's get the flag length. All right, so now we'll know how long the flag should be. And what we want to do is send a full, as many, we want to, I think how to describe this. We want to round, so like if the flag is, maybe it'll help if or maybe I'll just make it more confusing. If the flag is 28 bytes, we'll use that same example where I had, so the flag was 28 bytes. Like we can't just prepend 4 bytes, right? We knew we wanted 4 A's to eat it up, but if we just did 4 A's, what would happen is the flag will start here, and we can't. Like we can only decrypt when we know everything but the last byte that we're putting in a block. So what we actually want to do is round up to the next nearest size. So it divisible by block. So if we have 28 as the length of our flag, we want to start out with 32 A's. So that would give us 2 full blocks of A's. And then we have enough room to get everything done. So we'll end up, our final message will, the last thing we send, we'll have 4 A's in the front, all our known stuff, and then the, that's it. And then it'll have the, we'll be looking for that byte there because we're sending it A, and then it's going to concatenate the flag with that. So the flag will end on, or sorry, the blocks will be evenly divisible, and that last block will have that. So we're going to have too many A's on the front at the end, but we don't care because, you know, what does it matter? We just want to make sure we have enough A's. I don't know if that made it any better, but so we want it to be, we want our dummy block to be basically the next highest multiple of 16 greater than the flag. So we could do that by saying we want to know how many blocks the flag is. So if we floor divide it by 16, that'll tell us, like, in our case, it would say 1, you know, normally it would be 1 point whatever. We're going to drop it down to 1, and then we need to add 1 more block. So that's how many blocks we want it to be. And then each block is 16 bytes, so we multiply that by 16. And then that works also if we are less than a block. So if the flag length was 15, we'd get 0, but we still want a whole block. We get 1, we multiply by 16, we get 16, and then that's how many A's we want. And then the other thing we want to make sure and do is when we did it back, oh great, when we did it back the earlier way, we were just looking at the I guess I didn't have one of those. We were just looking at the first block, right? The 0 to 16, like the first 16 bytes. So what we actually want to do now is look at the full length of, we actually could figure out and just look at a specific block and compare specific blocks, but then we have to work out what block we're actually always looking at. I mean, it'd be the same every time, but it's just easier to take the first X number of bytes. But the way we'll do that then is we'll just have something called actually it would just be however long dummy is. So we could just say, let's just call it, I might be overcomplicating this, but let's just call it the length of the dummy. So that's that's like the window we're looking at when we're going to compare. So now we would do the same thing, except now we're going from 1 to the length of the flag, because we're not just doing a block, we're doing to the length of the flag. We want to send, or what we want to, yeah, we still want to send everything. We want to do that. We're doing this the same, except now what we're doing is we're going up to the window, which in our case is the length of dummy. And it might make more sense to just use the length of dummy, but when we make that the next harder case, this will actually work better. So hopefully this runs. And ooh, did I not put a bracket on the flag, or did it get it wrong? Oh, it did not get the last byte. Why did it not? Oh, I know why. Because it doesn't include those. So we would actually want to do like that. There we go. And that's just because, oops, if the flag length is 28, right, the end is, it's not included. So now we know we can solve that case. Now let's go back and let's do our more complicated original case where we're prepending some random thing. And it's not actually really going to be that much harder now if we just think about it for a second, because what we're doing is, I'll just do it here. Now instead we're going to have some gibberish in the front, some random gibberish that we don't know. But really all we have to do, right, is we still want it to be, we want full blocks. So what if we just, so we know in this case, what was it, 12 bytes I think is what it was of, oops. Yeah, 12 bytes. So here's our 12 bytes of 12 bytes random. What if we just pad it with 4 more A's, right? That gets us a whole block. And then we'll do the exact same thing we've been doing before. We'll get the length of the flag. We'll do everything the same. We're just always making sure that we're going to prepend this in addition to everything else we just did. Which isn't that hard, right? All we have to do is we'll start out with our dummy block. I'll use P's for padding, right? We know we need 4. Oops. That really should be the only thing we have to do different. Well, that, and now, right, we need to add the prepended bytes to our window. And actually, we will need to subtract those prepended bytes from the length of the flag length as well. So we should be good now. Now I'm just going to actually, I'll add a couple Pwn tools commands just to make it look good. Because like in the real challenge, this is going to take a while to run, and we want to have some kind of output. So and I'll do another one. And then we'll put it, we want to have some kind of update so that basically we're not just staring at a blank screen wondering whether or not it's working. So and then we'll tell it what byte we're testing. And instead of printing the flag, we'll just say there we go. Oh, so I have it. So this is after the CTF is over, but I have it. So, but I set up a server where I just put a little delay in it to sort of kind of simulate what it would look like. Because again, like I said, I'm a big dork and it is exciting to watch the thing slowly go through. So this is the flag from the challenge, and this still is going way faster than it would if you were doing it in the actual challenge. But I don't know, like I said, it just gives me a big rush. So hopefully you enjoyed this. I hope you got something out of it. I hope I explained it well. I hope I didn't make it more confusing. But I really like these kind of challenges. I think these are the kind of challenges that really, at least for me, is what can get you hooked on crypto. And so hopefully you got something out of this. And if you made it all the way to this for the exciting finale of the flag being recovered, oh, no, I printed it wrong. And then we didn't get the last byte of the flag. I'm some kind of off by, oh, I know my off by one error. Well, that's rather anticlimactic, but in a way, I oddly feel it's fitting. So yeah, I'm off by one error, and I spelled success wrong. So that kind of sums up my channel in general. Thanks a lot. Take care.